everyone, and welcome back to my channel. This is Sean from HFR, and if you're watching this video, then you're participating in HFR learning series. This being the second video in that series, and by popular vote, we are going to discuss oscilloscopes. Now, on my bench, I have a little oscilloscope kit that I bought off of Amazon, a DSO068, very cheap oscilloscope. Not really much use practically, but it was a fun kit to put together, and it does provide us some things. So I would say that it's not useless, but as well a more hobbyist version up in the upper right hand screen. This is a Siglent SDS 1052 DL Plus digital storage oscilloscope with a fairly decent 50 megahertz bandwidth and 500 megasamples per second, which 500 megasamples per second isn't anything really to write home about, but for general purposes, that's the oscilloscope that I use in all my videos. Now, what is an oscilloscope used for? Let's first ask that question. Well, generally, concerning maintenance or electronics, using a device such as a digital multimeter for AC/DC measurements, as well as the other measurements I discussed in the first video, is suitable for doing the bulk of your troubleshooting. However, when it comes to testing or troubleshooting of complex systems, or doing electronic type fabrication and design work, oftentimes an oscilloscope is needed. And as you've seen in a lot of my videos, I use an oscilloscope to see a waveform over the time domains. That way I can actually have a physical example of, or a visual example of that waveform and how it looks, which is very important, which is probably the primary purpose for an oscilloscope. It's a laboratory instrument, commonly used to display and analyze waveforms of an electronic signal over time. And if you caught the videos where I was looking at our pulse code modulation for our remote controls, again, a signal over time. If you recall the videos, restorations on the AM receiver, that vintage radio, we were looking at an amplitude modulated signal over time. And then in a general sense, with a lot of the audio devices, amplifiers, etc., that you see me work on, we're looking at a AC waveform, and sinusoidal waveform, that audio, and how it is represented over time. So that is kind of in a nutshell what an oscilloscope is for, although there are plenty of plethora of other uses, and we'll go over a few in this video just to demonstrate some of the things. Now, before we get into oscilloscope specifics, let's first talk about oscilloscope leads. This is your most common lead that you will use on an oscilloscope. This is what is often referred to as an oscilloscope probe or a probe. Okay. Now, common probes are going to have a nice fine point tip. A lot of times they'll have an amplification select switch, either 1 by or 10 by. So if you're needing to look at low-level audio, or you could do so, as well as a ground clip, which is most often needed in a lot of applications, and then several attachments such as the one I just stuck on that allows you to have an alligator clip type point for connecting to say the legs of a component on a circuit board and being able to go virtually hands-free on your probe. Now, these aren't the only type of probes that you can use, or devices that you can connect to an oscilloscope. You can also use a device such as this, although it's very uncommon. It's a typical BNC to alligator clip. Most often these are a 50 ohm cable, so you need to keep that in mind, as well as a traditional BNC to BNC 50 ohm cable. The impedance of which is actually very important because these scopes are usually 1 meg ohm impedance, whereas these types of, I wouldn't call them probe, but connectors, cables, are 50 ohms. So something to keep in mind. So first up, we're just going to take a quick look at this little kit oscilloscope. Like I said, not something I really ever bring out. As a matter of fact, I'm not quite sure if it still works, but we'll find out here in a second. But basically, you have your voltage range right here, very limited, 10 milliamps, 10 millivolts, 100 millivolts, and 1 volt range. I can't remember what 1, 2, and 5 was for. I think that had something to do with scaling, and then ground, AC, and DC, your references. And we'll get into all that, as well as being able to change your vertical and horizontal positions, slope, hold, level, etc. And then a knob for turning on and adjusting. But we need to be able to power it up, so I've got a little battery bank sitting here, and it's still charged up. And we'll see if this guy will power up for us at minimum. And it looks like it's going to boot. Probably a bit washed out on the screen here, so we'll try to see if there's a way for us to compensate for that washed out picture. Maybe if I turn off my overhead light. That actually made it a bit worse, so I zoomed in and you should be able to see this a tad bit better now. Alright, now that we've got it powered on, right now we have it set to ground, and that is basically how you're going to first set up your oscilloscope, and then you're going to set your reference line for ground. So on your vertical position, you may or may not be able to tell there's this little triangle here on the right side of the screen that moves up and down, and that's basically going to establish where our signal is going to come across on our graph. I'm going to put this more towards the center. We'll leave it there for now. And now I've also realized not just do we have voltage selecting here, 10 millivolts, 100 millivolts, 1 volt. This is a multiplier, so we can go from 1 volt to 2 volts up to 5 volts. Now, I'll leave it on 2 for now. So what I want to do is we're first going to use this to make a DC measurement. Now again, my reference is set on the center. I have this set to ground. And for this type of measurement, I'm going to use this probe right here. Well, unfortunately, as I was hooking it up to my DC power supply and testing out this oscilloscope, I wasn't getting a signal, and that reminded me of why I actually stopped using it. I blew out the input. Perhaps a troubleshooting video for another day, but instead, we're going to move over to the Signet digital storage oscilloscope that you see in the right hand corner, and we'll actually run through probe compensation, etc., and go through the same things that we would have done on here, because AC and DC measurements, setting up your voltage and triggering, etc., is all basically the same that you'll get with this, plus many, many, many more things. So let's move over to that guy. Well, apologies if my voice sounds a bit congested, because quite frankly it is. It is December here in Oklahoma, and it gets cold in this state. And with 4 kids, they get colds, and mommy and daddy get colds as well. And because of kids, it's like a smorgasbord of petri dishes and all kinds of things with all the kids and them running around in school and stuff. I'm also using the lapel mic right now instead of my traditional overhead condenser microphone, so the audio quality is probably not that great. But I wanted to be able to move around and my voice not fade in and out as we do some things on this video. Anyways, so I've got my 1 megohm Oscilloscope probe plugged up to channel 1 on my digital storage oscilloscope. Okay. Now, when I turn it on, I can actually turn on and off channel 1. That's something for you to recognize. But the first thing we need to talk about is probe compensation. Okay. Actually, before we even do that, you also need to make sure, see on my probe here, I've got it in 1 by instead of 10 by. I want to make sure that my probe is also adjusted for 1 by 2 on my oscilloscope. There we go. It was already on there, but you know, just different functions, things that you should keep in mind. Now, it's currently coupled to ground. That's that way I can make a ground reference since we need to compensate our probe a bit. We'll put it on the centered radical, okay? And then I'm going to use this, I know it's going to be hard for y'all to see off camera, but at least with this oscilloscope, there's a 1 kHz tone in the ground. And then we will take this probe and attach it as such. Ooh, bumped the camera there, did not mean to do that. I've got my Logitech camera I usually have canted out in the corner, precariously sitting on an extendable arm. But anyways, that's now attached. And then I'm going to go from ground to not DC, but AC. Now, we can go ahead and make an annotation here. You see how when I put it to DC, this is higher up than when I'm on AC? Well, right now, my waveform is in reference to my ground line. So given this AC, it goes above and below, right? However, if I was to couple it to DC, then it's going to shift upwards north of the ground. It's not, you traditionally don't do that when you're making audio or waveform measurements. You would traditionally put it to AC instead. But in some occasions, you could just switch it over to DC. You definitely will have an effect. Look at my voltage measurements on your math. If there's the ability to do internal math on your oscilloscope. So just something to keep in mind. This is actually not a 3.16 volt AC 1 kHz tone we're seeing here. What we're actually seeing is a 1.64 volt sinusoidal AC waveform. Okay, so you need to know what you're using, especially if your SIGGEN has the ability to do math for you. Actually, we should let me turn that off. Let me go to my measurements menu, and we'll just clear all measurements for now. All right. Now, with probe compensation, what you're trying to do, we can increase my voltage scale. We'll span this out a bit. Is you're trying to have a very nice square wave, essentially. You don't want to see any rounding or roll off on your trailing edge or leading edge, etc. So, how do we compensate? Well, it's best to have a, let's see, I think my overhead camera messed up for a second. We're back on? There we go. All right. It's best to have like a little tuning wand, something kind of like this. Non-metallic shafts, that way you're not basically adding capacitance to any devices as you touch it from your own body. Little metal tip right here. If you got plastic wood, you can use that as well. But on your probe, as I pointed out earlier, is a little fine adjustment. And let's see what occurs as I adjust it. As a matter of fact, I'm going to switch this to 10 by. And we're going to change our probe range to 10 by. And do this one more time. And now with this, we can see the importance of compensating on our probe. All right, let's compensate again. There we go. You see those changes? This is counterclockwise. This is clockwise. And now we've compensated our probe correctly. With that little fine adjustment to have a nice waveform. Switch it back to 1 by. And we'll bring this down. All right, pretty easy. Also want to show you something else here real quick. Again, Oscilloscope has a measurement function. So let's go to voltage. Instead of Vmax, we're going to set it to volts peak to peak. And then I'm going to add. Now on the bottom left hand corner, you'll see that 32 volts peak to peak popped up. But I'm still in 10 by, even though I set this to 1 by. So let's change this to 1 by. All right. Point number 2 or 3 or whatever point number. You need to make sure that if you're on 1 by here on your probe, that you're also on 1 by here, because that has an effect on your math. But look what happens if I switch this to 10. Now saying I have a 400 millivolt. Well, you'd think that 10 by would amplify, but that's not what is actually occurring. What this is allowing you to do is take greater voltage measurements through your oscilloscope probe. So if you have something that you can't bring in to full scale, vertical, full scale on your oscilloscope, you switch it to 10 by, and then what that does is that attenuates that signal by a magnitude of 10, so that way you can now get it onto your oscilloscope display. However, if you're making measurements as well, you need to also make sure that internal to your oscilloscope, you've compensated there, so you're getting a correct reading. Pretty easy, should make sense. And this kind of covers AC measurements. You can also consider the fact that we are on the 500 millivolt scale, right? And so if I went 1, that's 500, that's 1 volt, 150, 2 volts, 250, 3 volts, we are at approximately 3 volts. Make sense? And we can also do frequency measurements, at least with this oscilloscope. I'll go ahead and show you that. We go to time, we go to frequency, we click add, and it's telling us we got a 1 kHz frequency coming through the oscilloscope. But there's another way to do that. We're on our horizontal scale. It's in seconds to what, nanoseconds or something. Well, you could do that same measurement counting left to right. Or I'm currently at 250 microseconds, and you would, let's see, can I move this vertically, position it somewhere? Let's see, we got from trailing edge, we got 1, 2, oh, we're drifting off. Let me adjust my trigger and bring my trigger down some. The importance of the trigger is to get a steady waveform that's not going to drift. So I'm going to bring this trigger down. Alright, hopefully we don't start drifting again. And then sometimes, depending on the device you're using, you might have to use an external trigger as well. But for those of you who will ever have to use that, you're going to have a manual with alignment guides that say, hey, you need to use an external trigger. It's going to walk you through how to set that up. Well, we're on the 250 microsecond scale, going horizontally. So if we count 1, 2, that's 250, 500, 750, 1. So we have to go the full cycle, right? And then the inverse of that is 1, which means that we are at a 1 kHz signal. So the inverse of time is always going to be your frequency. You can always just plug that into a calculator too. However, we have another way that we could do voltage measurements and frequency measurements. On my oscilloscope, I have a cursors menu. Let me turn that on. I'll send it to manual. And you see these 2 white bars that populated? Okay, now I've got to remember for a second, how do I move them? I think it's with this. Yes, it is. Right now I'm on cursor A. I'm going to go to falling edge here, over to cursor B, falling edge here, and look, it's telling us our frequency. That's our delta T, delta over time, inverse delta over time, or however you want to call that. But there we go, 990 microseconds, 1.01 kHz. So we can make a frequency measurement that way. Let's change it from time to voltage. Go back to cursor A. This will be a peak-to-peak voltage. I'll put this at the bottom of my waveform. And cursor B at the top of my waveform. And we're at 3.3 volts. Fairly close with the automatic math that's being generated by the SIGGEN itself. But there could be reasons why you would want to do a manual measurement versus an automatic measurement. Especially if you have frequency changing between each revolution or full revolution of your waveform, such as with pulse code modulation. So you would measure from either trailing edge to trailing edge or leading edge to leading edge of your waveform and determine the frequency between the different peaks. Hopefully that makes sense. So that's more or less AC voltage and frequency measurements. What else am I going to use an oscilloscope for concerning AC? Well, let's talk about the visual representation of the frequency itself. As a matter of fact, I now have it coupled to my signal generator through those connectors, and my 1 megohm probe and BNC to Gator clips come out of the SIGGEN, sending out a 1 kHz tone at about 4 volts in amplitude, and we see that corresponding over there on the SIGGEN itself. Watch what happens as I change my frequency. Okay, I'm going to change my step value for my control knob to 1. Hit enter. And you see what occurs when I start decreasing and increasing that frequency. My wavelength gets a lot shorter as I increase frequency, and my wavelength gets longer as I decrease frequency. Go back to 1 kHz audio waveform. Now what if I do the same thing for amplitude? change that to say 0.5. See, as I decrease my voltage, my amplitude decreases on my SIGGEN. And as I increase voltage, my amplitude increases on my SIGGEN. Now, when I'm physically looking at my waveform, there are some things I'm actually checking out. You often hear me say, well, that's a nice sinusoidal waveform. So I am looking from peak to peak, and I'm making sure that there is no dips or distortion or any indication that the waveform itself is askew. Okay? No cutoff in the frequency, nothing like that. So you could potentially have, with a multimeter, a 4-volt peak-to-peak measurement, or as we also learned, you could measure a 1 kHz tone with a multimeter, but the frequency could actually look pretty terrible. So the oscilloscope gives me the ability to actually see the waveform and a little bit more in-depth diagnosis on how it looks. As a matter of fact, if I mess up my probe, see if I can jiggle it a bit here. You see that nastiness right there? That would not be a good waveform. So as a bit of a representation, that's basic AC measurements and diagnostics. What would you be doing this on? Well, AC voltages, lower level AC voltages. Max input you have is 4 volts max, so you're really not going to be plugging this into a wall outlet. But mostly around your audio ranges. This is a 50 megahertz oscilloscope, so I could get up beyond audible range into the RF range, low RF, and I would need to see those frequencies, in which I could do. Now, could I go to a frequency above 50 megahertz? No, not with this oscilloscope, because its bandwidth is 50 megahertz, unless through a non-linear device I heterodyne 2 frequencies. Remember when we heterodyne, saw the difference in 2 originals? Say I took this 60 megahertz frequency and heterodyned it with, I don't know, a 40 megahertz frequency. Well, the difference would be what? 10 megahertz? Well, the difference I can display up on this oscilloscope, and I can still do a waveform comparison to see if my waveform looks okay or not. That is something that you can do. Not something I can really demonstrate here because I don't have that really the Benchtop device to modulate that signal correctly to produce and show for you. But that's pretty much it for AC waveforms. Let's look at a DC signal on our oscilloscope. Before I test for a DC voltage using the oscilloscope probe, I'm going to do a couple things. I've set my coupling back to ground, and I'm going to put that near the bottom. If preferably you'd have it at the very bottom, but for demonstration purposes, I'm going to put it right about here. Now I've set my benchtop power supply to 5 volts DC, so I'm also going to adjust up my voltage scale for 1 volt. And we should have an increase of 1, 2, 3, 4, 5. 5 volts should be about there. And then my coupling is going to be set to DC. Let me hook up the ground. There it goes. And now I'll hook up that. There we go. Now you might say, well, why am I measuring 120 millivolts? Well, if you remember on the measurement menu, when we added voltage, we did volts peak to peak. Let me add in a voltage max. And now we have our actual DC voltage. I bumped my probe a little bit there, or maybe that was the DC power supply. But yeah, again, basic DC measurement, pretty simple thing. Now, why wouldn't I leave when I go back to, let's see, why would I not leave this on the center of my display, you might ask? Well, with the DC measurement, obviously it's a straight line. Got set to 1 volt. Let's count. 1, 2, 3, 4. It's probably not going to display. See what happens. Yeah, now it's above where I can see it, but I have to bring my reference down to be able to see that DC signal again. Well, when it comes to a DC waveform, or DC waveform, a DC signal, what am I actually looking for? Essentially that it's not dirty. I have a nice defined line here, and I'm not seeing any scraggly anything sitting within here. Well, maybe we can kind of demonstrate a dirty DC signal. Well, if I had dirty DC, it could look something like what you see now on the display. I'm still sending in a 5 volt DC signal, but I have messed with it, messed with that DC signal a bit using a post trap that basically turn it into dirty DC. Because it is slightly varying, you'll actually see up on the oscilloscope it's measuring that 5 volt DC is 7.2 volts. I mean, it's just messed up the measurement. Now, if you were to use a multimeter, you say, well, my DC reference voltage is 5 volts, but I'm measuring 7. It's a bit high, but it could be maybe it's good, or maybe you're still measuring 5, or slightly above 5 or below 5 and thinking it's good. But unless you actually see that voltage over time, how would you know if it's dirty or not? Obviously, if this was my regulated, and what regulated DC means is it's a DC waveform that shouldn't have any ripple on it whatsoever, like the ripple you see here. But obviously, if there's ripple on my DC voltage, that can wear out your components over time. And so it's definitely something else that is worthy of checking when you're diagnosing fault on a circuit board and you're looking at DC voltages. Yes, you can just use a multimeter. Sometimes you probably want to actually throw it up on a scope to see how it looks. Is there ripple on it, or is it a nice clean waveform? So let's see what can we do. Noisy DC. Here we go. Here's some noisy DC. And we got different kind of different things that we can see on our DC voltage. Here's a multi-tone. This is essentially, say your regulated DC was near an audio source or something, some form of inductance was occurring on that DC line. There's not enough shielding, you could get something like this on your oscilloscope. But yeah, there you have it. And that's in a nutshell what I look at when I'm looking at DC on the oscilloscope. Well, we've done AC and DC measurements and functions on an oscilloscope. I'm pretty sure there's more things that could be done, but for the purposes of this video, very basic. We'll just leave it as such. I mentioned amplitude modulated signals. I want to show you a few things on that. And in order to do that, we're going to need a tad bit of a higher frequency. I don't know why that was messing up on me so much, but we essentially got it now. Got a 1,800 kilohertz frequency being generated by a signal again, and I'm going to modulate it at 1k hertz, 80% modulation, and there we go. It's probably because I didn't have it turned on and off up here. Yeah, there we go. That's the reason why I was messing up quite a bit. But anywho, I'm gonna change my horizontal scale a bit. And yeah, let's see if we can trigger to get this thing to get still on a jumping around so much. All right, there we go. We got it as steady as it's probably going to get for now. But there goes our 1 kHz tone modulating that 1800 kilohertz signal at 80%. Now, I know it's at 80% because I said 80%. I can change it to 90%. Can you see how the corresponding waveform, uh, our upper and lower sidebands increased and we decreased right here in the center? Well, let's say you're working on an AM radio and you're looking at the modulated waveform that it's producing, but you need to do a measurement. You need to measure the percent of modulation and adjust it to somewhere between, say, 85 and 95%. You'd probably pick about 90. But all you have is the display on your Oscilloscope to go off of. How would you make that measurement? Well, again, we can go to our cursors menu, turn it on, manual, and instead of time, we're going to go to voltage, and let's move channel A. Oop, wrong one. What am I thinking? Channel A, we're going to put to the lower portion of this peak. Channel B. Oh, I'm doing the wrong thing again. There we go. To the top peak. And we've got a delta of 3.08 volts. I'm going to write that down. And now that I have that written down, now I want to measure where I'm closest together on my waveform. So let's move channel B down, my cursor to right there. And then channel A cursor, we're going to bring it up to right about here. I'll drop that down just a wee bit more. Oops. Always have a tendency to do that. They'll moving this knob, moving this one down here. So let me set this back up a wee bit better again. There we go. And our new delta is 300 millivolts. Okay, there is a formula that we can use to determine AM modulation depth. Well, the formula for that is as such. Percent mod equals E max minus E min over E max plus E min. So our max was 3.08 volts and our min was 300 millivolts. And what that would come to is, let's see, 3.38 and 2.78. And I divide these two numbers together. I'm going to pull out my calculator for that. And here we go. 2.78 divided by 3. Oh, I forgot a number. 3.38 is 82% movement. So over twice, 82% modulation. Well, That's a bit lower than my SIGGEN is saying it's sending out. I wonder if that's because of how I have these things connected. I'm going from a 50 ohm cable to 1 meg ohm cable, so I have impedance mismatch. As I move it around, you can see that modulation dropping in and out. Maybe that's the issue. Maybe we need to go the entire way on a 50 ohm cable. Let's swap those out. Well, we've changed it out, and I went ahead and made new measurements, and we got 3.26 volts as our max and 0.330 volts as our minimum, or 330 millivolts. And that comes out to 2.93 and 3.59. Let's put that into our calculator here. 2.93 divided by 3.59, 0.181. Move the decimal places over twice, and we have our percentage. So, yeah, I would say that definitely an impedance mismatch, but looks like our SIGGEN is not accurate. So that's something I'll need to keep in mind. Now, whether that's just a characteristic of a cheap programmable signal generator or whatnot, but yeah, the math is math. You get modulation and multiply it by 100 to get your percent, and we're showing 81% modulation. To be honest with you, typically when I'm looking at a 90% modulated signal, it's going to look a wee bit more closer, something more around that line right there. That's what I would expect. Now, they do make modulation meters that can give you, that can tell you what your modulation is at. And basically, those modulation meters will spit you out a indication of 80 or 90 or whatever percentage, right? But again, why would we want to look at this on our oscope? Well, when it comes to modulation, you could have modulated output, but again, the signal, the actual waveform might not look correct. As a matter of fact, in a lot of amplifiers, when transistors in the power amplification section start going bad, you'll start to get very weird waveforms. So let me change it to what a square wave 1 kHz waveform looks like. Yeah, I've never seen anything really like that. But nor this triangle, nor this up ramp, nor this down ramp. Let's see. Can I give myself a bad modulated signal? Yeah, I mean, that's probably about the closest I've seen triangle waveform when it comes to band modulation. But you'll definitely be able to tell. You're not going to have a nice sinusoidal waveform. It's going to look pretty jaggy or off kilter. As a matter of fact, if I put this back onto my oscope 1 meg ohm probe and this other connector here, we might actually be able to kind of fault it out and demonstrate that example. Let me do that. Okay, I think now I can kind of show you a better example of a bad amplitude modulated waveform. As a matter of fact, when I squeeze these cables, you can kind of see that it's causing that the oscope to, catch up with that signal coming in. But you see how we kind of make that signal asymmetrical on one side just by turning the cable a little bit. Traditionally, when you have bad modulation, your waveform is going to be very asymmetrical. But I think that would be a decent example. But again, you can have a modulation meter still telling you you're at 80 or 90 or whatever, but physically seeing that waveform is very important. So we've done what, AC now and DC. We've looked at a modulated waveform, AM modulated as an example. What's some other things that a oscilloscope can do for you? Well, this one has the ability of providing measurements. We've seen them, but you can do a lot more measurements. We have multiple voltage measurements we can turn on, multiple time-based measurements that we can turn on that may be beneficial for whatever device we have on test. We know that our trigger is here to kind of get our signal to steady out. And again, you could use a second probe plugged into this external. You can external to a device, to an external device, trigger to an external device. You see this run stop here. Right now I've got this recording, as you see over here, so it's constantly in run mode, so you can see that signal. But you could do a single sweep over in the right hand side. If you needed to just capture something, you've paused it. Now, if you remember from the troubleshooting I did on the remote controls and that pulse code modulated signal, I had essentially pressed a button to try to capture that signal up on my my oscilloscope. What's some other things? Well, that's mostly what I use my signal generator for. I think I've got something that might interest you as well. Give me a second. Okay, we're going to start talking about something or demonstrating something that I think is actually super cool. I mean, if you're not going to get cursor controls and stuff like that on something like this, automatic measurements, etc. The bandwidth on this is so minuscule, you're not going to see AM modulated waveforms, but as well, Lissajous patterns. For those of you who do or do not know what those are, I think they're absolutely wonderful, and they can give us quite a bit of additional ability to troubleshoot not just the phases of our signals, but also potentially components as well. So what I've done is I've set my SIGGEN to output a 1 kHz tone at 4 volts peak to peak on channel 1 and channel 2. And if I turn on channel 1 on my oscilloscope, you can see that. I'll turn it off, turn on channel 2, you can see that exact same signal. As a matter of fact, let me turn them both on. Now, traditionally, your vertical scale is controlled by your voltage adjustments or vertical adjustments, and then your horizontal scale is controlled by your time base or horizontal adjustment. Okay, and the horizontal scale will have an effect on both input signals, but the vertical scale has an effect independent signals, as you can see right here, or independently on each input. However, we can change our device from a YT format to an XY format, and now our horizontal scale is being controlled by an input, and so is our vertical scale being controlled by an input. And this, let me tell you, this is super cool. So what we're going to do is I'm going to change the phase of my input signal coming in on channel 2. Now, instead of thinking that our signal is going over time, left to right or right to left, or however it's coming in, I want you to think that our signal is now a dot, and it's now spinning out from center. Okay? That's how we're going to view this. Now, since they are both of equal amplitude and in phase, let's start taking channel 2 out of phase. And we're going to take it up to 45 degrees out of phase. And look, 45 degrees out of phase, we're going into an upward slope and oval shaped signal. Let's take it to 90 degrees. We're now 90 degrees out of phase and we have a perfect circle. Let's take it up to 135 degrees out of phase. We're now oval and we're on a downward slope. Let's take it to 180 degrees. Oh, a bit too far. I don't know why it's jumping from 79 to 80 right there as I move this, but we'll just make do with that. But now we're on a downward slope and everything is, back in, well, not in phase. It's 180 degrees out of phase, but it looks like they are in phase. If we take it out of XY, this is how it would look on our oscilloscope at 180 degrees out of phase. Let's keep going. We go from 180 to 225. Oh, I think I went a bit too far. 225. There we go. We are back to a oval on a downward slope, but it's our signals have kind of flipped, if you could think about it like that. But now let's go up to 270. All right, we're back to a circle at 270 degrees out of phase. Look at that. They're still not on top of each other. Well, we've got a circle. Let's go up to 315. We're now back to a forward slope and somewhat circular and oval. We'll take it out, look at it. You can see that our waveforms are starting to come back into phase. And yeah, will this let me go up to 360 degrees or essentially back in phase? Yeah, we go past that point. And we'll take it out and you can see that they're perfectly aligned up again. So that's pretty cool. And if you're used to looking at Lissajous patterns on your oscilloscope, then you can most definitely spot phase difference between your AC waveforms, and that can be potentially good with troubleshooting, especially audio alignments and stuff, where in your waveforms must be out of phase in order to not cancel each other out. Just something to think about there. But what about component troubleshooting? Oh, something else I forgot to show just for gee whiz before moving on to component testing. We saw as we changed the phase of channel 2, what happens if we change the frequency? Let's go back to XY mode, and I want to change the frequency of, let's see, input channel 1, let's change it to 2 kHz. And look what we have. We have a bow tie pattern. And let's see what happens as we continue to change that frequency. And it starts to get a bit jumbled up, but pretty cool things. And we could do the same thing over here on channel 2 as well. Let's see what occurs. Hey. All right, let's change this to 2000 hertz. I was doing something a bit weird there at first. But yeah, we got a bow tie pattern this way as well. Well, if we change our amplitude. Okay. Anyhow, let's move on to components and Lissajous patterns. Okay, component level troubleshooting. Let me turn off this gen for a second, just on the display, and I'll turn off the oscilloscope too, and just show you what I got going on here. Essentially, I made a pretty simple circuit. Our SIGGEN is set to 100 hertz at 10 volts peak to peak, okay? And the positive side of my output signal is going to the top here, negative side going to the bottom here of whatever probe or connector I have hooked up to my SIGGEN. This one, 50 ohm cable BNC on one end, gator clips on the other. And then tied to the negative rail is going to be channel 1, channel 2 ground. It's on the negative rail. I've got a 10 ohm resistor going in between that to channel 2 positive of my 1 mega ohm probe. And then the device under test, in this case, a 510 ohm resistor, and then channel 1 going to the top part of that resistor. Now, that's basically kind of like a simple octopus or something along those lines, but we can look at this using our oscilloscope in the same XY mode. Now look at there. Essentially, your horizontal scale is your voltage scale. So if we were to count these out, we should be able to see that we're 10 volts across. And our vertical scale is our amperage. So traditionally, when you're looking at a resistor, you're going to have that forward slant. Obviously, if it looked pretty terrible, say that the waveform or the display of our signal wasn't in that type of pattern, we could potentially have a bad resistor. Let's check out some other things though. I kind of want to grab went ahead and pre-pulled out a couple of diodes. We'll first look at a 1N4148 switching diode. Let me decouple this and this guy right here and this guy right here. Make sure I orient my diode the correct way, cathode and anode. Alright, I think that's making a decent connection. We'll put channel 1 probe back and channel 2 probe back. And let me go back out of my display. I think I knocked out channel 2 there. Yeah, I did. Come on now. There we go. Channel 2 is back. Yeah, it would have been better to build this off a breadboard, but it is what it is. And here's what our diode looks like. And we can see the forward bias voltage right here. That's because I'm bumping my probes. So if I keep my hands off them, but we can see our forward voltage here. Unfortunately, my oscilloscope does not allow me to turn on my cursors when making this type of measurement, but you could measure the forward voltage of your diode and check it. But traditionally, your diodes are going to look like this. Let's swap it out for a what's the other one I got? A 1N5819 Schottky diode. So let's try that. And here we go. Here's our Schottky diode. Looks like our forward biasing voltage is a little bit less on this. I think that's to be expected, but yeah, there you have it. What's there to say about this? You would compare those forward biasing voltages with whatever data sheet you have for those components, and you can make those measurements. Something I don't have a Zener diode on me, but if I did, you would actually have a reverse biasing voltage as well, and a kind of a trailing edge going down this way. Probably hard to see with the way I have it, but kind of like a tail coming off over here. But yeah, there are multiple different things that components that you could. This is just a few, but you could test with this type of setup to see if those components are functioning as they should. So I don't know, something pretty interesting to look at here. And definitely, I feel something worth showing to all of you who are watching this video and learning about oscilloscopes and some practical uses of them. Well, ladies and gents, that's pretty much going to do it for our second video, part of the HFR learning series. And hopefully I don't have to wear this pretty crappy lapel mic again. So I do apologize for the audio quality of this video, but I had to use my boom stand for my condenser mic for this camera sitting right here to get it to face the oscilloscope sitting up on my shelf. Anyways, yeah, that's enough rambling about that. I really hope you enjoyed this training and kind of a somewhat basic look at a digital oscilloscope. And you know, there's an awful lot more things you can use them for and do, and there's a plethora of videos out there across YouTube that you can watch. So you know, take mine for what it is. It's not the entirety of everything you could do on an oscilloscope, but at least it's somewhat provided for you here, a part of the My Mate Vince fan club, and all you've given to the community. And hopefully you learned something along the way. If you enjoyed this video, please consider subscribing to my channel if you haven't already. And you know, if you want to do something similar, use this video as a guide, by all means do that. And then if you're inclined to, you can also donate to my channel. There's a PayPal in the description. With that being said, just like the first video, you do what you want. I'm not here to beg. I'm just here to add to this community. This is this community was put together for Vince. He's an excellent guy. I really appreciate the content he puts out there. Very, very engaging, and I don't want to hinder anything from over on his channel. So again, this video will be unlisted, so that way I won't accrue watch hours, etc. to my YouTube channel. and may eventually add it to Patreon if I decide to do turn HFR learning series into a patron subscription service, but we'll see. That being said, I appreciate the fact that y'all watched. Hopefully you've learned something along the way. I know I'm rambling on. This video is probably way long enough. Take care. Goodbye.
Mark?